Hello everyone, and thank you for joining. Today I will talk about a self-supervised approach to anomaly detection for rotating machinery. The main goal is predictive maintenance in real sites, especially where labeled fault data is limited. Please note that this presentation is a fictional sample created for video demonstration purposes. To begin, predictive maintenance is attractive because unplanned downtime is extremely expensive in manufacturing. Low-cost vibration sensors are now widely available, and public datasets have helped machine learning research move quickly. But on the factory floor, every site is a little different, so methods that work in one place do not always transfer cleanly to another. The biggest practical issue is that normal data is everywhere, while true anomalies are rare and expensive to label. Now, moving on to the main challenges, conventional approaches still have several weaknesses. Threshold-based methods often depend on expert judgment, so they need to be tuned again for each machine and operating condition. Supervised learning is also hard to apply because fault examples are too scarce, and even when deep models perform well, maintenance teams still want a clear answer to why a machine was flagged. So our approach is to learn only from normal vibration data. We first convert the waveform into a time-frequency representation, then learn a useful feature space through contrastive learning. After that, we model the distribution of normal behavior in that latent space and use it to assign a continuous anomaly score. To make the method more practical, we also account for operating mode, apply robust data augmentation, and use explainability tools to highlight the frequency bands behind each alert. Next, let's look at how the method was evaluated. The study covers pumps and fans, using both public datasets and several months of continuous field data from a partner plant. The proposed method is compared against simple thresholds, one class SVM, and an autoencoder baseline. We focus on AUROC, F1, detection delay, and false positive rate, because accuracy alone is not enough in a real maintenance setting. The results are encouraging, especially on field data. The proposed method achieves the best AUROC, and it improves by 0.11 compared with the autoencoder in the plant setting. Just as importantly, it detects faults much earlier, cutting detection delay from 19 hours to 11 hours. That is about a 42% reduction, while keeping the false positive rate at or below 0.05. That said, the method is not a perfect fit for every case. It works best where there is plenty of normal data, relatively stable operating conditions, and faults with clear spectral signatures such as bearing issues or misalignment. A practical workflow is to pre-train on public data and then fine-tune on a few weeks of site-specific data. Current limitations include slower response to abrupt impact, like faults, difficulty defining operating modes for frequently changing equipment, and explainability that is helpful but still not fully sufficient for operations teams. To wrap up, this study suggests that label-free anomaly detection can be practical for field deployment. It delivers strong accuracy without requiring anomaly labels during training, and it also provides earlier warning time for maintenance planning. Looking ahead, the next steps are to handle more sudden fault patterns, learn operating modes automatically, and improve explanations for operators. The evaluation code and pre-processing scripts will be released after the talk.